Today we are looking at finding the average atomic mass of things. So remember on the periodic table that number that is underneath the symbol, and we talked about why it's a decimal number instead of a whole number. That's because that was the average of all the isotopes, right? Today we're actually going to do that calculation, and then we're going to go ahead and move into the mole concept. And it's going to be fast because we all know how to go from moles to atoms and grams to moles and all that kind of stuff, right? So this is, again, we are in pure review mode right now. Nothing we're doing today is anything different than your Chem 1 experience, regardless of the level. So looking at this data has relative masses of our different isotopes, and then over here it's got the percentage abundance of those isotopes in nature. So this is the same as doing kind of a weighted average. If you look, our isotopes are neon 20, 21, and 22. The actual mass of neon 20 is 19.992. I have 20 things in the nucleus, though. Can anyone remember? We did this, and we'll do this again later. But why isn't it just 20 AMUs? Why is it 19.99, Naira? It converts mass to energy, yes. Why does it do that? Kate? To keep the nucleus bound together. So this is mass defect, and that mass is put toward nuclear binding energy. So that's why they're giving us this additional number right here. If you're not, for some reason, given the number, you can use the 20 if you have to, okay? But they actually gave us the actual mass without the defect. So to do this, you do a weighted average. We take that first percentage of 90 and turn it to a decimal, 0.9092, and we're going to multiply it by our first isotope. This is just like calculating your grade, right, in the class. You take your percentages of your categories and you're going to add them up. And we're going to add it to 0.0257. I'm just going to caution you here. So many students just want to say 0.2 because they forget. You got to move it over twice, that decimal, so watch yourselves. We're going to multiply that by 20.994. And then we're going to add it to our final weighted average, 0.0882 times 21.991. And we're going to add those up. Now, just what I want you to round to. I want you to round to whatever our givens are in, okay? So it's a really, really large percentage of 19, so it shouldn't be much higher than 19. It should be probably somewhere between 19 and 20, at the most in the 20s. So what do we get? 20.656. I heard a bunch of you say that. Thank you for being on it. Let's do this all period. And the unit, that little U stands for atomic mass units, AMUs. That's not a common unit that we use. We want a usable number. Atomic mass units in the real world don't mean anything. So we like to look at the periodic table and treat it as grams per what? Mole. So if we have a mole of these atoms, a mole of them, 6.02 times 10 to the 23rd of them, they would actually weigh 20.656 grams. And so the grams per mole is an acceptable unit for atomic masses as well. And it's actually the more common one. Right now we're just looking at it at the atomic level, so that's cool. But in class we need to be in grams per mole when we're doing dimensional analysis with moles and stoichiometry and all that stuff. Okay, so let's move on to a different one. Do y'all have questions about this one? Pretty easy? Yep. Okay, so in this one, same concept, a little bit different in that they want us to find the weight of the second isotope. So we have two isotopes of chlorine. They give us the percent of one with its mass, and they're like, okay, what's the mass of the other isotope of chlorine? So what information can we infer? There's something we need to infer from this problem. There's something we can figure out from what they give us without, we're missing something. Yes, Matthew. The atomic, well, the average atomic mass of chlorine, we do need that, because what are we going to set this equal to? What else can we figure out? That's kind of what I wanted to start with, the percent of the other isotope. We know this isotope is 75.77%. There are only two isotopes according to this problem, so what is that isotope? 30 what? Or 20? 24.33, is that okay? 23, math is hard. 24.23%, and that's an important thing. So when we set this up, like Matthew said, we need the actual average atomic mass to set it up and solve for the unknown isotope's mass. So where do we get that information? Periodic table says the average atomic mass of chlorine is 35.453. This is from the periodic table. All right, and we're going to set that equal to, then, the percent times the mass of each isotope. So the percent of the first isotope is 0.7577 times the mass of the isotope of 34.9688. God, that's a lot of numbers. 34.96885 plus the percent of the other isotope, which we subtracted from 100 to get, 0.2423 times what? X, and that's what we're solving for, okay? So what does X end up being? And as far as what to round it to, choose the one with the least. We can't be any more accurate than any other value. So right now, we've got this to the level of 3 decimal places based on the average atomic mass. So let's give me 3 decimal places with our answer. 966 or 967? It really doesn't matter. If you were off that way, I'd be okay. So that would be AMUs or grams per mole. I'm okay with either one of those. Okay? So I'm only going to do these 2 examples. This is where doing your homework is important because there's going to be some different approaches or different questions that the problem may ask, one of which was they gave you masses of the isotope, the average atomic mass, and are telling you to find the percentages. Does anyone remember how to do that? Where you have to find the percentages, both of them. So I would have this number here. I would have, I don't know the percents. I would know a number here, and I would know a number here, but I'd need these percentages. And then this I'd have a number. Does anybody remember how we do that? Matthew? Perfect. We put X in here for an unknown value, and we know that this other isotope has to be 100% minus whatever this percentage is. Well, what's 100 in decimal form? 1. So we do 1 minus X here, and then you'd solve. The only thing to be careful when you're doing that is make sure you associate the percent with the, oh, I meant to put that there, the percent with the appropriate isotope. So just watch where stuff is coming from. Okay? All right, mole concept. Now we're going to get into the mole. A mole of a compound can be recorded in particles, number of atoms. We can also figure out a mole based on mass. And the mass of 1 mole of any substance we can figure out by adding this stuff up on the periodic table, average atomic mass. So whenever we're converting from grams to moles, that's what we need to be able to do. And then you need to know Avogadro's number, which tells you how many elements are in a molecule. It can tell you how many in a mole of a molecule. It can also tell you how many molecules are in a mole of molecules. So that number is just like a quantity. So if I say a dozen, you think what? 12. If I say a mole, you think 6.02 times 10 to the 23rd. It's a really big number. So when we do these mole problems, you remember we start out in Mole Town. That's in the center of everything we calculate. Today we're going to go to 2 places. We're going to go either Gram Land or Particle City. Particles being molecules or atoms, depending upon what your starting material is in. So who remembers how to get back and forth from Mole Town to Gram Land? Naira. Yeah, go to the periodic table and find what? The grams per mole, the average atomic mass. So we're going to find the grams per mole from the periodic table. And so whether we multiply or divide, oops, so that's the wrong side. Holy cow. Grams per mole. Whether or not you multiply or divide, do not memorize that. That's ridiculous. What you're going to do is use dimensional analysis, and you're going to have so many grams over 1 mole. It's always per 1 mole. So this you can flip in your dimensional analysis to make things cancel. So do not memorize the whole multiplication division thing. If we're going from particle city, our conversion factor is different. What is it? Isabel? Avogadro's number. So we're going to have 6.02 times 10 to the 23rd molecules, atoms, particles, tires, whatever, that thing over 1 mole. 1 mole is going to have that much of anything in it. Okay? And again, don't memorize multiplication or division. We're using the tool of dimensional analysis. So you're going to see it's going to be really, really easy to set up. So let's just jump in and start doing some problems. I want you to base your sig figs on your given. Okay? And then as far as molar masses goes, you can pretty much round to whatever, but in class, I would like us to, when we're using the periodic table, just round to 2 decimal places. And the reason I picked 2 decimal places is because the periodic table on the AP exam, every single one of them is rounded to 2 decimal places. So I'm just trying to get you used to 2 decimals. So starting with starting with grams here, we have 18.0 grams of C6H12O6. So I'm in gram land. I want to get to moles. Any ideas? Go ahead, Jacob. Atomic mass of the compound by adding up all the elements. We spent a half a day covering how to do that last year. Now I expect you to know how to do it. So let's go. Let's get that molar mass. For every 1 mole of glucose, I have, no, not 1,200. Ooh. 180 point, check your math, 180.18. Yeah, it's a little off. It's okay. We all make mistakes. I have no problem. I'd rather you try and mess up than not try. All right, so when we do this, we want to round our final answer to 3 sig figs. And what is it? Really? Yeah. Okay, cool. And what is that? What is the final unit? Moles. Okay, let's go the other direction and go from moles to grams. When they ask for weight, they're looking for grams. Make it simple. Don't be like, oh, I'm going to do kilograms just because. Just make it grams. 4.50 moles. What is the formula for barium sulfide? Ide. It's just BAS. That's okay. If it's ite or 8, we would change that. But see how this is a prime example why we need nomenclature, right? Because if we name it wrong, we get the wrong molar mass, and that's going to lead to the wrong number of grams. So for every 1 mole, I need to find the grams by looking at the periodic table and getting the molar mass. Has anyone gotten it yet? Did you say 169.39? So 39 is fine. Grams of barium sulfide for every 1 mole of barium sulfide. So my moles cancel, giving me grams, and we're done. I don't know why I continued my little thing. So to 3 sig figs based on this 4.50, what are our number of? Nice, 762 grams. All right, let's look at number 3. I really like number 3 and 6 kind of together because they address different issues. Number 3 says, how many molecules are in 28.6 moles of nitrogen gas? What is nitrogen gas? N2. Do you see why they use the word molecule there? Because it's N2. Okay? So we just need to convert this to molecules. So we're in mole town. We want to get to particle city. So we're going to use Avogadro's number. So in our little dimensional analysis, for every 1 mole of N2, I have 6.02 times 10 to the 23rd molecules. And what do we get? Someone else get that? Just making sure. All right. Since it's going to be published on YouTube, you know, we want it to be right because everything on the internet is right. And then that's going to be molecules. I write molecule short, like molic. I got to put the C on there because if not, it looks like it's moles. Now, Here's the thing that's this year I'm going to kind of start questioning you about. I want to question you about the common sense of your answers, okay? If your question is molecules or atoms or whatever, you're going to expect a pretty gosh darn big number. So these big exponents make sense. But if you're solving and the question asks for grams and you get a gram answer that's 10 to the 29th or something, probably not. Probably not the right answer. It's got to make some logical sense. If I ask you for number of molecules and you get 0.07 molecules, what? First off, molecules don't run around in halves. Secondly, they're usually really tiny, so we deal with them in very large numbers. So ask yourself, does my answer make sense? All right, this next one I chose specifically to follow up. Do you see a difference in those two questions in 3 and 6? Yes, what is the difference? This is asking for atoms, that asks for molecules. So we're going to have an additional step. Because when we solve this, which we're going to do first, we're going to get to, when we multiply by Avogadro's number, what are we actually getting after one multiplication of 6.02? We're getting molecules, right? That number only takes you to the smallest unit that your original answer is in. So we need to then do an additional step. So for every 1 mole of O2, I have 6.02 times 10 to the 23rd molecules. But that didn't answer the question. Now I have an additional step. What do I have for every 1 molecule of O2? 2 atoms of O. Do y'all see that? So there's a difference there. So I need you to watch for that when you're doing your problems. So we're going to round to 2 sig figs on this guy. And again, big number. What do we get? Times 10 to the what? 24th. Is that someone else? Did a bunch of people get that number? Atoms of O. Okay? So please watch your cells when you're looking at what they're asking for. Okay, so those are simple one-step problems. Before I move to 2 steps, do y'all have any questions? Yes, Samantha. Yes, it would be. Thank you for catching that. It is 2 sig figs. Any other questions? Yes, Amelia. Yeah, y'all, that's too many problems for us to do. So I'm choosing select problems from the packet to work. So yeah, we are skipping through a lot of these actually, especially the 2-steppers. I kind of want you to get to working on your homework quickly here so you practice on your own. Me standing up here doesn't really make you get it. So let's go ahead and do number 6. Number 6 says, how many molecules are in, and molecules is kind of to say because this is actually an ionic compound, so there's really no such thing as a molecule. We usually say formula units, but it's semantics at this level, so don't worry about it, but I just want you to know the truth. So how many formula units are in 937 grams of calcium acetate? So 937 grams, woo, calcium acetate, what's the formula of that? 2. Calcium's +2 and the acetate's -1. So that is where that is coming from. I sure hope I'm getting sound. I see it responding to my voice. I just did it in a different order, so I'm a little nervous. Okay, so I'm in Gramland. I need to get to Particle City. What do I have to go through? Mole Town, so I got to go to moles. So I got to convert this for every 1 mole. I'm not going to rewrite the calcium acetate just because it's really big. I have how many grams? So let's get quite a few of you attempting this so we can get the right number to 2 decimal places. I suggest a lot of you to try this, or most of you, because remember we have that 2 outside that acetate, and how that means we have 4 carbons and 6 hydrogens and 4 oxygens. 158.1? 178, so 18 grams. Thank you. That's how many grams we have, so our grams cancel, and now we're in moles. Now how do I figure out how many molecules or formula units I have? Avogadro's numbers, is that what I heard? Yes. So for every 1 mole of this stuff, I have 6.02 times 10 to the 23rd molecules or formula units. So when I solve, I need a number rounded to 3 sig figs. Is that correct? Did I write it down correctly? 3.57 times 10 to the 23rd? 24, thank you. 24. Okay. So let's ramp this up a little bit, shake things up and jump to number 9, because I think number 9 is a little bit more of a challenge. How many atoms of chlorine, are in 654.5 grams of calcium chloride? So starting with the given, and it's 4 sig figs, I'm going to do grams of, what's the formula for calcium chloride? CaCl2. Now, I don't want you to think too far ahead in the process. You can't get to number of anything, molecules, atoms, formula units, whatever, until you're at moles. So when you're giving grams, you're going to have to go to moles first, so let's start with that. So for every 1 mole of calcium chloride, I have 110.98 grams that we got from the periodic table. So my grams cancel. Now what do you guys want to do? Yes, go to molecules. For every 1 mole of this guy, I have 3 molecules. Oh, not 3. My bad. 6.02 times 10 to the 23rd molecules of our calcium chloride, or formula units, actually. So our moles cancel. Now I'm in molecules. But what do I want? Atoms of chlorine. For every 1 molecule of CaCl2, what do I have? Yes, 2 atoms of Cl. So we got to get to the smallest unit based on what's given. We're given molecules here. Avogadro leads to molecules. If we were given atoms initially, it would lead to atoms. So that's why we're adding that additional step. All right, to 4 sig figs, what is our answer? That? Atoms of Cl. What? So are you writing or typing?
I'm writing.
Writing.
That's why I have it like that.
I was just curious. I believe you. I was curious what's easiest, and like also. You're right. So what are you writing with? What? I know that. I know you're using your finger. What tool? What app? What? Notability. Okay. See, I loved DocAS, so I don't know. Really? Yeah. Apparently the owner of DocAS either closed it or isn't ever contacting us, so we couldn't get group deals, so they didn't use it. But Notability will have to be tried by me. So you like your finger better than a stylus?
Honestly,
Yeah?
yeah. Stylus is really
Interesting. Okay. Couple more problems. I want to do, let's do 11. How many grams of magnesium are in 5.55 times 10 to the 26 molecules of magnesium sulfide? So we start with our 5.55 times 10 to the 26 molecules of, what's the formula for magnesium sulfide? And again, it should be formula units, but I'm trying not to think about it. Okay. So now we need to somehow get to grams. But to get to Gramland from Particle City, we need to go to Mole Town. So for every 1 mole up top, we have 6.02 times 10 to the 23rd on the bottom. Now that's in moles. I'm going to kind of just give you the trick now just to, because it's one of those things I've just learned to do off the cuff when I'm doing problems like this. I want just grams of magnesium. How many grams of magnesium alone, right? If I were to go from moles to grams straight, it would be to grams of magnesium sulfide, which then I guess I could do because then I could subtract off mg from it and get, but to me that's messy, right? So what I want to do from here, what is this mole? These are moles of the full thing, right? What I can do is break it down even further. This is also a mole ratio. It's 1 to 1. So for every 1 mole of this whole thing, how many moles of just magnesium do I have? 1. If I have a mole of automobiles, cars, how many moles of steering wheels do I have? 1. If I have a mole of automobiles, how many moles of tires do I have? 4. Okay? So that's kind of what you're doing. You're using these numbers as mole ratios as well. So for every 1 mole of MgS, I have 1 mole of just Mg. So that allows me now to get grams by just multiplying by the molar mass of the Mg. For every 1 mole of Mg, what do I have? 24.31 grams. Great. Y'all seem like you're a little more on it. I don't know, first period's just tired. I know what I'm going to do with them. Because they're not as... A quote from Roy, if anyone out there is curious. No one is as good as second period. I'm just quoting. All right. So 2, 3 sig figs, what do we get? Okay, I'm not a big fan of numbers like this. I kind of want it in scientific notation. I would take it, but it's irritating to graders because most people will write in scientific notation on the AP, and I'm like, when they do this, I'm like, because then I have to count, and that's giving me more work. And when I'm grading 800 papers a day, and I already want to rip my face off, this makes it worse. So let's do 2.24 times 10 to the what? 5th? Isn't it 4th? And what was my final answer in? Grams of magnesium. And there's my answer. All right, good job, y'all. So go ahead and start your homework. Homework tonight is crucial because I didn't do very many of these, and I didn't do very many atomic mass unit things, and mole calculations is the crux of this entire semester. It's kind of like breathing in chemistry, all right? So I want you to breathe. So make sure you do the homework. If you're struggling, come in and I'll work the problems we skipped with you. We can do some additional practice with those if you need to come in and see me.